Good morning students. Today we will discuss chemical properties of dihydric alcohols. These dihydric alcohols, they are also called as commonly glycols. So these are dihydroxy components of alkanes. Their journal formula is CnH2n plus 2 O2. So the simplest and the most important dihydric alcohol is ethylene glycol. So ethylene glycol, they are classified as alpha, beta, gamma glycols according to the relative position of two hydroxyl groups. Alpha is referred to as 1,2-glycol and beta is referred to as 1,3-glycol and gamma is referred to as 1,4-glycol. So ethylene glycol is referred to as alpha glycol, that the position which bears OH group, it is alpha with respect to this functional group. So in this case, in the propylene glycol, the position of this hydroxy is beta with respect to this functional group. So next is the nomenclature of dihydric alcohols. The dihydric alcohols, they are also named as alkane diols, and the trihydric alcohols are also named as alkane triols. So if we have this example, that is ethane 1,2-diol, and another example is that is of trans cyclobutane 1,2-diol, and also in the next example is that of pentane 2,4-diol. Here the position of hydroxy is 2 and 4 with respect to the particular positioning of the functional group. And next we have 3,3-diethyl heptane 1,6-diol. Here at the position 3, two ethyl groups are attached and there are two OH group, one is at the position 6 and other is at the position 1. So the name is accordingly 3,3-diethyl heptane 6-diol. Second is the methods of preparation of dihydric alcohols. So they are prepared by different methods. So first is the preparation of diol from ethylene. So when ethylene is reacted with IC dilute alkaline Bayer's reagent, which is dilute KMnO4 in the presence of alkali. So this will give us a diol, and the process is called as synhydroxylation, that both the OH moieties are on the same side of the carbons. So if alkenes are reacted with carboxylic acids, they first give us ethylene epoxide, substituted epoxide is formed, and which upon hydrolysis gave us the product where it is called as anti-hydroxylation. Both the OH are on the different sides of the carbon-carbon bond. So next method of preparation is that is with oxygen in the presence of silver metal. So alkenes, they react with oxygen in the presence of catalyst silver at a temperature of 200 to 4 degrees centigrade, gives epoxide, which upon subsequent acidic hydrolysis gives us ethylene glycol as the product. So next we have the very important topic, that is the physical properties of glycols. So dihydric alcohol, it exhibits the following type of physical property. First is the physical state. Here it is. It is a colorless viscous liquid and sweet in taste. Its boiling point is 470 Kelvin. If we compare its boiling point with boiling point of ethyl alcohol, that is 351.5 Kelvin. So here the difference is due to the presence of extensive intermolecular hydrogen bonding in ethylene glycol. Second property is its solubility. So it is miscible in water and ethanol, but it is insoluble in ether. And here the principle is like dissolves like. So third property is its greater solubility in water is also due to the same reason, that is the extensive formation of hydrogen bond. So this ethylene glycol is widely used as a solvent and also as an antifreeze agent. Next we will discuss the chemical reactions of vicinal glycols. So first is the action of sodium. So ethylene glycol, basically it is made up of two primary alcoholic groups joined together. So if we react ethyl alcohol with sodium at a temperature of 50 degrees centigrade, it is converted into a monosodium salt of ethylene glycol. And further upon heating the monosodium salt of ethylene glycol, the other hydroxy group is also substituted by sodium atom at a temperature of 160 degrees centigrade. Then there is a formation of a disodium salt of ethylene glycol with the evolution of hydrogen gas. So second reaction is the reaction with hydrogen halide. So by reacting ethylene glycol with hydrogen chloride, it gives us, upon at a temperature of 160 degrees centigrade, it gives us a ethylene chlorohydrin as the product. And when further ethylene chlorohydrin is heated with HCl at a higher temperature, that is at a 200 degrees centigrade, both the hydroxyl group here is substituted by chlorine atom. So it is converted into, the monochlorohydrin is converted into that is ethylene dichloride. So next we have action of ethylene glycol with phosphorus halides. So if ethylene glycol, it is heated with phosphorus bromide, the ethylene dibromide is formed as the product along with the formation of phosphoric acid. So next is the reaction of diol with aldehydes and ketones. Here if the glycol react with aldehyde and ketones in the presence of PTSA, that is para-toluene sulfonic acid, it gives us cyclic acetals or ketones. So this reaction is widely used to protect carbonyl group. Vicinal glycol, or you can say ethylene diol. Ethylene glycol reacts with aldehyde to give us a 5-membered acetal along with formation of water molecule. And similarly ethylene glycol with ketone, upon reaction with ketone, it gives us the protection, and the compound form is that of a kettle along with the removal of water molecules. So the water is formed by 2 hydrogens of the glycol and 1 oxygen of the aldehyde or a ketone. So next we have oxidative cleavage of 1,2 glycols. So when they are treated with periodic acid HiO4 or lead tetraacetate, glycols undergo oxidative cleavage by breaking of carbon-carbon bonds to yield carbonyl compounds. The oxidative cleavage of 1,2 glycols with periodic acid is known as Malparade reactions. So ethylene glycol with LTA or periodic acids gives us 2 molecules of formaldehyde. Next is the mechanism of oxidative cleavage of glycols. So when we oxidize glycols with periodic acids, oxidative cleavage takes place through a cyclic intermediate formed by attack of periodate on a glycol. So when periodate attacks the glycol, there is a formation of a cyclic 5-membered cyclic intermediate esters. So this bond breaks and there is a formation of 2 carbonyl groups along with the separation of IO3 negative as the iodate ion. So 2 carbonyl compounds are formed. So when we have oxidation of diol with lead tetraacetate, this also occurs through a same cyclic intermediate formation that will undergo an oxidation reduction process leading to the cleavage of carbon-carbon bond. Here the diol is forming a cyclic intermediate esters and the 5-membered lead ester is formed. So there is a breakage of this carbon-carbon bond and the formation of double bond in between these 2 carbon and oxygen, and also the formation of double bond between these 2 carbon and oxygen. So it gives us the formation of 2 carbonyl compounds and 1 lead diacetate molecule is eliminated. So next we have pinacol-pinacolone rearrangement. This is a very important rearrangement reaction. Here the first time this rearrangement has been observed in a pinacol. Pinacol is 2,3-dimethyl 2,3-butane diol. So this is commonly called as pinacol. This pinacol rearrangement was the first molecular rearrangement. So here pinacol is converted into pinacolone in the presence of acids. So here if we have this pinacol, which is also called as 2,3-dimethyl butane 2,3-diol. So this upon protonation gives us the formation of a, first step is the protonation of the hydroxyl group. So protonation can occur at either this hydroxyl group or either at this hydroxyl group. So both of the positions of the hydroxyl group are equivalent. So it gives us the formation of first is the protonation, and in the next step it is a reversible step where there is elimination of water molecule takes place. So then there is the formation of a tertiary carbocation. So we know the tertiary carbocation is a stable cation, and another thing is there is a formation of this OH, that the lone pair of electron of OH bond is get shifted to this carbon OH bond, and there is a formation of a double bond. So this is also called as, here we can say that the positive charge is stabilized by delocalization of a heteroatom resonance. So the positive charge of the carbocation is stabilized by the heteroatom resonance. So this structure is further more stable. So this structure is only formed by 1,2-methyl shift. So one methyl group is shifted from this position to the carbocation position. So this will give us this intermediate, which is a very stable because of the heteroatom resonance. So you can say that further upon deprotonation, that is the removal of a proton, this intermediate is converted into pinacolone, so which is also called as the conjugate acid. So it is the product of repeated rearrangements catalyzed by the proton transfer. So whatever the acid we have added in the first step, that proton has been removed in the last step of the rearrangement. So this is about very important pinacol-pinacolone rearrangement, which takes place only in pinacols, that is the vicinal glycols. Thank you.